Okay, so the next thing we want to do is look at how acid and base salts affect the pH of a solution. So just to go back over, a salt is the product of an acid-base reaction. And so it's an ionic compound like this. So for example, if I take sodium hydroxide and acetic acid, I'll form sodium acetate and water. And it turns out the sodium acetate can have an effect on the pH. And this is how it does it. The acetate ion can react with water in a hydrolysis reaction. So that's what this is called. And this is actually called acid-base hydrolysis, I think, in your book, this section. But in the hydrolysis water reaction, the acetate removes a proton from water, and what you get is you get the acid back, plus you get some OH minus. And this is how it affects the pH. Now, technically, if you take something and you add it to water, and it creates the conjugate acid and hydroxide, this is known as a KB reaction. So the question is, how do I get Kb for acetate ion? Because if you go to that table that I showed you in the back of the book, you won't find Kb listed for acetate. All you can find is Ka for acetic acid. So what I'm going to show you is how you find the K values for the conjugate bases or acids of different neutralization reactions or for different acid-base salts, okay? So first of all, let's start with writing the HA, the acid ionization reaction for acetic acid. So this is equal to H plus H2O, and that's going to be equal to hydronium and acetate ion like this. And then I'm going to write the Kb reaction. A minus plus H2O equilibrium with HAC, so that's AC minus, plus OH minus, like this. So this is Ka, and this is Kb. Now watch what happens when you add these two reactions together. I always thought this was really neat how it worked out. The HACs can cancel. They'll be on both sides of the reaction. And the ACs can cancel because they'll also be on both sides of the reaction. So what does that leave us with? This leaves us with 2H2O on the left side in equilibrium with hydronium and hydroxide. And what is that reaction, right? Well, it's Kw. And so if you add, going back to the initial equilibrium chapter, if you add two reactions together, right, the equilibrium constant of the reaction that you get is just the product of the equilibrium constants from the reactions you got it from. That maybe sounded harder than it actually is. It's just Ka times Kb, like that. So for acetic acid, Ka is 1.75 times 10 to the minus fifth. So Kb for the acetate ion, its conjugate base, would be 1.00 times 10 to the minus 14. That's Kw divided by Ka, 1.75 times 10 to the minus fifth. So that's 5.7, I think it's 13. Let me go double check real quick. Yeah, it's 5.714 times 10 to the minus 10. Three significant figures for this one. So that's the Kb value for acetate ion. So now if you have a problem and it says, for example, calculate the pH of a solution of, let's say, 0.1 molar sodium acetate, this is where you get the equilibrium constant from. So here's the problem. It's calculate the pH of 0.1 molar sodium acetate. And in this problem, what you need to start to get good at recognizing is that acetate is the conjugate base of acetic acid. So this comes from HAC. Now, you're going to need, because this is the conjugate base, you're going to need to do a base hydrolysis reaction, and you're going to need a Kb value. And that's what we did on the previous slide. But I wanted to make a point about how you know what to look up. If you're dealing with the conjugate acid of a weak base, right? How do you know what to look up? You look up whatever has the neutral charge. So AC minus is got a negative charge, of course, and then this is my neutral form. And so that's what I'll look up. And what you'll find is you can only find the Ka value. Now, this is a Ka value. I've used this one for years. I don't know if it matches the one in your book, but it's pretty close. But that's the value for Ka. It's not the Kb you need for the reaction. So then you have to go calculate what that value is, like we did in this previous example here. Okay, so first let's write this reaction out, and I think it's important that you write these things out. And for now we're ignoring the sodium, but you can't always ignore it. So for now we're just going to ignore the sodium. So I have AC minus plus H2O. That's going to make HAC plus OH minus, and then I'll have my initial, I'll have my change, and I'll have my equilibrium. Now, AC minus concentration, because it comes from the sodium acetate, is 0.10, right? And this is a soluble salt. You remember the term soluble salt? When it goes in solution, it completely dissociates into its ions. So the molarity of the sodium acetate and the acetate ion are the same. And I'll assume there's no acetic acid in the solution when I first dump it in. And then the acetate ion is going to want to get its proton back. Because remember, acetic acid is a weak acid. It doesn't like being ionized. And so it wants to pick up that proton. So we're going to go like this. We're going to go minus x. Oops, didn't mean to do that. Oh, I guess I can't undo it. I'll just draw another line in. Be minus x, and then 0.10 minus x. This is going to be plus x and plus x here. So I just have x and x. And this should look like really familiar to you by now, but this is my Kb reaction, and I'm going to end up getting x squared over 0.10 minus x. Now, what is my Kb value? I have to calculate that. So I'm going to do Kw divided by Ka. And that value ends up being 5.7143. And it has 3 sig figs, so I'm just carrying some extra digits in my calculation, times 10 to the minus 10. Now, when I look at this problem, I say to myself the exact same things I always do when I do these problems. Can I approximate this, right? And the answer is yeah, because this concentration is way bigger than the equilibrium constant, like 9 orders of magnitude, 9.5-ish, anyways, or 8.5-ish, but still, it's quite a bit larger, the concentration. So I'm going to approximate. So that means x is equal to square root, and just like for acids, for bases, it's going to be concentration times Kb. So I'll plug those values in. There's my concentration. There's my Kb. I plug that in, and I'll get 7.5593 times 10 to the minus 6. And 3 sig figs, so I'll just mark it and keep track of it. Now, what is this value, right? And this is why I say it's important you do these all the time initially. It's both the HAC and the OH minus, so it's not hydronium yet. You're wanting pH, but the next step is to calculate pH. So you're going to say pH, or POH, is negative log of my X value. So I'll plug that in, and I'll get 5.1215. Like that. Now, pH is just going to be equal to 14 minus POH. And again, I'm going to get 8.87848 extra digits in there. I only have 3, so it's going to end up being 8.878 as my pH of my solution. Now, you can do a mental check on this, right? You added the conjugate base of a weak acid to a solution. So what should the solution pH be? It should be greater than 7. So is it greater than 7? Yeah, it's great. It's not a really strong, weak conjugate base. It's got an equilibrium constant in the 10 to the minus 10 range. So 8.87 is a little bit above 7, a little bit on the basic side, and that seems like that fits. What I was going to do here, and then I realized since I'm just recording this, I was actually going to talk about why we can ignore sodium, because that's a very important topic that's coming up in our next segment. And I am going to talk about it a little bit here, but I thought I would go ahead and do one for the conjugate acid of a weak base, since it's a recording, and you can either skip this part of it and go to the end, or just watch and go ahead and do it. Okay, so it says calculate the pH of a 0.2 molar ammonium chloride solution. Now, here's the thing. What is ammonium chloride? This is NH4+. It's ammonium ion. This is the conjugate acid of ammonia. This is a base. This is my acid form, my conjugate acid. So when you go to look up the K value, this is the neutral form of the two, you're going to be looking up Kb. Now, you find Kb, it's 1.8 times 10 to the minus 5th, and they're not all 10 to the minus 5th, by the way. It just seems like all my examples for some reason have that sort of, they're all about 1.8 times 10 to the minus 5th. That was kind of totally an accident, but what you need to do then is you need to set up your ice table for the conjugate acid. And since it's a conjugate acid, it does what acids do. It donates a proton to water, and it's going to make NH3 plus hydronium ion. It's a Ka reaction. So I'm going to, again, write all this out, because it's all kind of still a little new. I'll go ahead and drop these in here and drop that out. Initial change equilibrium like that. And this is 0.2 now. And this is minus x, and this is 0.2 minus x. Ammonia is initially 0, and a hydronium is initially 0 in these calculations. And then what happens is I get plus x, and then I get x, and then you should recognize this now. This is Ka is equal to x squared over 0.2 minus x. Now I just need to find Kb, or Ka from Kb. So Ka, like I did previously, is Kw divided by Kb. I looked up Kb. Well, okay, I just remembered it. But anyways, you would look it up in Appendix 2. And that would be equal to 5.55, repeating, times 10 to the negative 10. And again, the K is a lot smaller than the concentration, so I'm going to go ahead and do the approximation method. And again, it is still C times Ka. And that's going to give me 1.054. 1 times 10 to the minus 5th. That means my pH, again, is equal to negative log of x, because this is a hydronium generating reaction. It's a Ka reaction. So x is the hydronium concentration. That's going to be equal to 4.98. A little south of neutral, right? A little acidic, on the acidic side of neutral. So if neutral is 7, this is just below it at around, very close to 5. And 2 sig figs because my K value and my concentration only had 2 sig figs. Oh, I didn't think about that in my last problem. My concentration only had 2 sig figs 2, so that would be 8.88, like that. All right, correction. There you go. I hope that bothered somebody earlier.